I'm Hiroshi. I would like to talk about our recent work on RFID-based sensing technology with Microstrip line as a novel sensor. At first, I would like to talk about our motivation of this research. Inventory checking and stock controlling are important for efficient store management. Controlling checking and out-of-stock product reduces sales opportunity loss, but real-time inventory monitoring on store shelves is difficult. Inventory checking by human is very burdensome work, and it takes quite a long time. So new technology needed for this problem. Next, I talk about some technologies that solve this problem. Array of pressure sensor come up soon for sensing many materials on the seat. But fabricating many sensor nodes becomes complicated, and these sensor nodes are fixed by electric wire. And conventional UHF RFID system used mainly in the clothing stores and rental shops. And this system can check inventory automatically and immediately, but some critics say that it raises privacy concerns. And another problem is cost. Although cost of UHF RFID tag antenna is typically about 50 cents, this cost accompanies each product. And so this conventional UHF RFID system is difficult to apply to low price products. On the other hand, in our technologies, there is no need to stick a tag on each materials. RFID tags are arranged on the antenna sheet, and tag becomes as a sensor nodes. So there is no additional cost for each sensing product, and no worry about privacy. And cost of sensor node is about 50 cents. Reader-writer antenna and RFID tags communicate with near-field coupling. In other words, no need to connect sensor with electrical wires, so that we can easily change the sensor arrangements. Next slide, I would like to talk about operational property of this sensing technology. This picture shows the architecture of RFID-based sensing technology with microstrip lines. There is a spacer which secretly changes the coupling coefficient between the transmission line and RFID tags on the spacer. In this research, we use a commercial RFID tag named WebLite, which is produced by SmartLab Technology Group. This spacer exists for maintaining conjugate impedance of RFID antenna, which is designed for matching to the air. The antenna port of the RFID reader connects to the transmission line, and the end of the transmission line connects to the load resistance. And object nearby the RFID tags change the conjugate impedance of RFID antenna. There are important two interactions to the RFID tag. One is the near-field coupling between the RFID tag and the transmission line. The other is the plastic inductance and stray capacitance between object and tag antennas. So this page shows the relation of two interactions, which two interactions. The RFID tag antenna intercept power P tag is given by that's the equation, where P trans is the radio frequency power to the transmission line, which input from the RFID reader, where P trans is and G trans is the ratio of coupling power, which depends on the mutual capacitance and inductance between the tag antenna and transmission line. The power which RFID chip received is written by that equation, and where ZC is where the power reflection coefficient gamma tag is given next equation, and where ZC is the impedance of RFID chip, and ZA is the RFID tag antenna impedance at its feed line. An object which mainly made of metal and or dielectric, such as water, changes the conjugate impedance of tag antenna ZA. An object which mainly made of metal or dielectric, such as the object put passive inductance and storage capacitance on tag impedance when the object approaches the tag antenna, and it includes a metal ground of transmission line. Then power reflection coefficient gamma tag between the tag antenna and tag IC changes. RFID tag antenna impedance changes by the position relation of RFID tag antenna and the microstrip line. So important step for designing this sensor is adjustment of these positions. So next slide. In this slide, I will show actual example of adjustment of spacer. We use a polypropylene sheet as a spacer on a 50 ohm microstrip line, and place the commercial RFID tag on the top of the sheet. Vertical gap is the distance between the RFID tag and the microstrip of transmission line. At first, I will talk about only vertical gap. Horizontal gap is fixed at half size of the length of the RFID tag. The graph below of this slide shows the RSSI in millidecibel versus the vertical gap. When the region is distance is less than 5 mm, the level of RSSI gradually decreases because of storage capacitance of ground of microstrip lines. And when the region of distance is over 6 mm, the level of RSSI gradually also decreases because tag and microstrip are apart. And from this result, we choose a spacer thickness to 5.4 mm. And next attempting is investigating the characteristic change of coupling by the horizontal gap between the RFID tag and the microstrip line. This parameter mainly influences the kind of fields that concern about the coupling. RFID tag antenna that we used in this research has a meander line and a loop structure. Loop structure generates strong magnetic field, and edge of meander line generates strong electric field. And meander line has resonance characteristic that enhance the coupling coefficient. In this page, I will show actual example of adjustment of horizontal gap. The condition of experiment is the same with previous. Vertical gap is set to 5.4 mm. Horizontal gap in the figure indicates the distance between the center of the RFID tag and the center of the microstrip line. Graph in the left side shows the RSSI in millidecibel versus the horizontal gap in the case of water or the metal cans on the RFID tag. As a reference, an RFID tag with no material is also measured. When the region of gap is over 20 mm, the RSSI decreases because the tag and microstrip are gradually apart. When the region of the gap is less than 20 mm, the RSSI also decreases. For investigating the decreasing, we cut the meander dipole of RFID tags. Cross line in the graph is the RSSI versus horizontal gap in this case. As graph shows, the region of gaps is less than 20 mm. They inductively couples. And this direct inductive coupling does not change regardless of whether the frequency response of the tag antenna is changed. This coupling doesn't have sensitivity to the object, and sensitivity is very small. For this attempting, we decided horizontal gap to about 20 millimeters. The sensitivity of the proposed system to various materials listed in this table. Metal cans and the snack package have metal surface and have high sensitivity. Plastic bottle and paper package contain highly dielectric materials such as water, fruit juice, and milk has also have a high sensitivity. Thin books composed of papers are difficult to sense because the characteristic of the tank antenna on the seat remains almost completely unchanged. So this sensing system is suitable for detecting the metal cans, metal package, plastic bottle, and paper pack which contains water and so on. A demonstration of sensing system is shown in this page. This sensing sheet is covered with white cover sheet, and there is a RFID tag, a microstrip line, and spacer under the cover. The area of orange and blue squares shows the sensing position, which contain RFID tags. The interval of RFID tags are about 60 millimeters in both directions. 4 parallel 50 ohm microstrip lines are designed in the white cover of polypropylene. For example, various metal cans and plastic bottle are placed on the sensing sheet in this figure. Black dots on the monitor shows that RSSI is lower than the threshold value when materials are put on the seat at the corresponding position of the RFID tag. White dots on the monitor shows that there is no object on the RSSIs within the threshold value. In this figure shows the case of the other sensing objects. Thin aluminum foil and snack package are detected due to their metal surface. And this picture shows some pack of cigarettes, which also has a metal package with different sensing size of seed. With this sensing system, many kinds of items in stores can be detected, which cover drinks, packs of cigarettes, and so on. Future works, image processing for recognize edge of sensing objects, and decreasing sequence of sensing seeds with engineering antenna structure and transmission line. And challenging to apply this sensing system to many applications and show this sensing system improves efficiency of store managing and reduces the sales opportunity loss. Conclusions. We describe the design process of appropriate coupling, which is the key of this sensing system. And operation of this sensing set and detection of a variety of actual items was demonstrated. The RFID-based sensing technology with microstrip lines discussed can be applicable to inventory tracking with no low cost.